Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on amplifier. Okay, so for this video, I'm going to show it to you how can we actually plot the center and also the radius of the input and output stability circle. So this will be the objective of this video. Okay, before we come to the plotting of stability circle, let's understand when we need to plot this stability circle. For example, if the amplifier is unconditioned stable, which means that the amplifier don't need any specific condition for them to be stable, then we don't need to plot this stability circle because the amplifier is always stable. So the reason that we actually plot this stability circle is when the amplifier is condition stable, which means that we need to specify which condition then the amplifier will be stable. So when we actually plot this stability circle, we have actually two sectors. One sector called stable, another sector called unstable. So therefore, this actually specifies the condition, where the amplifier should be at so that it will be able to work in a stable region. So basically, this is why we need to plot this stability circle in order to distinguish the zone, where the amplifier will be stable or unstable. This will be the part 12 series discussion on amplifier. So guys, if you're keen to know more about amplifier, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on amplifier. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask your question through the comment. Before I continue, guys, I'd like to urge you guys to help me by like this video. If you like this type of content, please let me know by pressing the like button. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for your strong support. Let's quickly understand what is actually a stability circle before we go into the discussion how to plot the stability circle. The stability circle are actually tools that is used to examine and analyze the stability of an amplifier through a graphical techniques utilize a Smith chart. So basically, in short, we actually make use of Smith chart in order to plot the stability circle. And from the zone of the stability circle, we can determine whether the amplifier will be stable or not. So the stability circle can be determined in the region for the source and also for the load, where the amplifier circuit will be condition stable. So basically, as I mentioned earlier on, if the amplifier is condition stable, then we need to plot the stability circle for the source and also the load. If not, if the amplifier is unconditioned stable, so therefore we don't need the stability circle at all. However, simple tests can be used to determine unconditioned stability. So basically over this video, I'm going to show it to you how can we actually test if the amplifier will be unconditioned stable. One such test is the K, which is the K factor. We also have this, which is the determinant of the scattering parameter, or S parameters in short, which is shown over here. So basically they will show whether a device will be unconditioned stable, based on this Rollet condition. So basically this is the equation to determine the K factor. So basically when we actually calculate the K factor, if the K factor is more than 1, so it is potentially unconditioned stable. Only one of the factor, we need two factor. So basically when K is more than 1, so basically it meet one of the criteria to be unconditioned stable for the amplifier. So this is the first condition. Along with another condition will be this determinant of the scattering matrix. So basically under this equation here, if let's say it's less than 1, so if the two conditions meet, which means that K is more than 1, and this determinant of the scattering matrix less than 1, then the amplifier will be unconditioned stable. Keep this in mind when we actually have this situation when K more than 1 and the determinant of the scattering matrix less than 1, then the amplifier will be unconditioned stable. Then we need not to draw the stability circle at all, since the amplifier will be always stable. Okay, so this is the first condition that we need to know, okay, to determine whether the amplifier will be stable or unstable based on this so-called K to the determinant of the scattering matrix equation. Next, okay, if the device scattering parameters do not meet this criteria, okay, the criteria that I mentioned earlier on, okay, the device will be unconditioned stable. Okay, so once we have unconditioned stable, then we need the stability circle, okay, to determine the value of the reflection coefficient for the source and reflection coefficient for the load, okay, for which the device will be condition stable. So basically, when we actually plot this stability circle, it will determine the two sectors, as I mentioned earlier on, stable and unstable. And we also need to do a quick recall based on my previous discussion on part 11. Okay, basically, we must also meet this criteria in order for them to be stable, which means that the magnitude of S11 must be so-called less than 1, and the magnitude of S22 also must be less than 1. Okay, so basically, all these conditions, then the device will be unconditioned stable. Remember, beside the K, and then beside the determinant of the scattered matrix, okay, and then we also need to ensure these two things, okay, then we can declare that the amplifier will be unconditioned stable. Okay, while the K to the determinant of the scattering matrix test is a mathematical rigorous condition for unconditioned stable, okay, it cannot be used to compare the relative stability of two or more devices. Basically, this means that, for example, when we actually calculate the K, okay, or the determinant of the S matrix, okay, we cannot so-called guarantee, how to say, not really guarantee, okay, but we cannot compare, okay, how stable the device will be. Okay, for example, okay, when we actually design amplifier, okay, there will be a situation that the amplifier will be more stable than the other one. But when we actually do this K and the determinant of the scattering matrix, we cannot determine which amplifier will be more stable. This is what you want to say. Okay, because it involves constraint on two separate parameters. In short, for this type of parameters test, okay, which is the K to the determinant of the scattering matrix, we cannot determine which is more stable. But okay, recently we have this new criteria, okay, that basically will be able to tell which one is more stable. Okay, so for example, I actually have two amplifier. Okay, earlier on, as I mentioned, if we use a K factor and if we use this so-called the determinant of the scattering matrix, okay, I will not be able to tell which amplifier will be more stable. However, with this equation, okay, I can actually tell which is more stable. Okay, for example, under this case here, okay, basically when this is over more than 1, okay, which means that it will be unconditioned stable. Okay, in addition, okay, it can be said that the larger the value implies greater stability. So basically, in short, okay, the bigger this number, okay, you can actually say that this amplifier will be more stable. Let's say when they are actually under 1, okay, so the one that is closer to 1, okay, will be more stable than the one that is further away than 1. So in short, this actually gives us the liberty, okay, to compare, okay, which amplifier will be more stable as compared to the earlier on test, which can only tell us whether the amplifier will be stable or unstable. Saying so much word, okay, let's work out an example, okay, to understand this better. Okay, so basically keep this in mind. The objective is to determine the objective of this video is to plot the center and radius of the stability circle. So basically for this type of amplifier, most of the time, it will be so-called condition stable. Okay, so basically these are a transistor, the amplifier, basically they are having this S parameters over here. Okay, so therefore the first thing that we need to do is we need to determine whether the amplifier will be unconditioned stable or condition stable. So how we can do this is, remember, we need to do this test. We need to do the K factor test, and we need to do this determinant of the scattering matrix test. So let's do the determinant of the scattered test first. Okay, so basically this is the equation. Okay, so basically from the equation here, basically S11 will be 0.869 and minus 159. So basically this will be S11. S22 will be 0.507 minus 117. So this will be S22 minus S12. As you can see from here, S12 will be 0.031 minus 9. And then S21 will be 4.2561, which is here. So I work up this, okay, so that you can double check on your working. So basically you can do this, okay, either by calculator, okay, or you can actually do this in a simple as in the PC nowadays. Okay, so basically you can calculate that this is actually the determinant of the scattering matrix is actually this, because we just need the magnitude. So therefore the answer is 0.336. Okay, so basically this number, okay, is less than 1. So therefore we can say that this is actually unconditioned stable. Okay, one of the so-called criteria it meet. Okay, so therefore we can conclude that the amplifier will be stable rather than unstable. So basically this is the criteria that we actually first calculate. It actually meet the criteria since it's less than 1. So basically there is a so-called chances for the amplifier to be unconditioned stable. So next, okay, we are going to calculate the K factor. So this is the formula to calculate the K factor. Okay, so basically you need to do the magnitude of S11. The magnitude of S11 will be 0.869, okay, which is here. Magnitude of S22, okay, basically will be 0.507, okay, which is here again. Okay, so this is the determinant of the scattering matrix that I calculate on the previous page, which is 0.336. Okay, so therefore it's over here. So this part here, okay, you need to do a calculation. Okay, so basically you just multiply by S12, which is here, multiply by S21. Okay, if you calculate earlier on, if you see that I calculate earlier on, which is 0.1318, which is here, or 0.318 here. So basically this is S12 multiplied by S21 here. So I just copy this part over here. I just need the so-called the magnitude portion here. So if I calculate this, as you can see from here, the answer K will be equals to 0.383. And for this condition case, I need them to be, so called, if they are smaller than 1, then they will be condition stable. If it's more than 1, then it will be unconditioned stable, if you still remember what I have mentioned earlier on. Okay, so I mentioned earlier on, okay, in order for them to be unconditioned stable, the K must be greater than 1. Okay, but for this example, the K is less than 1. So therefore, it will be condition stable. Okay, for this criteria, it meet, but the K factor, they actually don't meet the criteria. So therefore, the amplifier is unconditioned stable. Okay, so basically, this is what I want to mention. Okay, for this case here, it meet the condition, but not for the K. So therefore, the unconditioned stable is not specified, and therefore the device is declared as potentially unstable, or we need to have a condition for them to be stable. Okay, let's look up this equation which I have shown you earlier on. So this equation will be able to determine how stable it will be, and basically this will be the equation here. So as I mentioned earlier on, if this is more than 1, then the device is unconditioned stable. For this case, we can always double check. Okay, so for this case here, I believe that this so-called this value will be so-called less than 1. Okay, if it's more than 1, then the amplifier will be unconditioned stable. Okay, but earlier on, as I calculate based on the K factor, okay, this actually indicate that the amplifier will be unconditioned stable. So this value, it should be less than 1. Okay, as I mentioned earlier on, the bigger the number, it implies that it is more stable. Okay, let's work out on this value here. Okay, so basically this will be the value here. So 1 minus S11, okay, again, the magnitude of S11, which is 0.869. Okay, this will be S22. Okay, S22 is 0.507 minus 117 here. Minus, okay, so basically this will be the determinant of the S matrix, okay, which I have calculated earlier on, okay, which is over here. Okay, so therefore I plot the number over here. So this will be the determinant of the scattering matrix. S11, okay, with the complex conjugate. Okay, what does this mean? Okay, so basically from here you can see that this is 0.869 with a negative. So basically I need to change the negative to positive. So therefore this will be the positive term, and this will be plus. So this term I worked out earlier on, which is 0.1318. Okay, so basically over here I just do this part here. Okay, so I think you should be able to do this. Okay, I just simplified these two terms. I multiply them together to get this term here. And then after this, basically, I will get the so-called the magnitude. This thing I'll combine. And then after that, I get the magnitude. And from here, I calculate that this value is 0.682. Okay, as I mentioned earlier on, okay, this value should be less than 1. If it's more than 1, then it will be unconditioned stable. Okay, but I have done the K and the determinant of the scattering matrix, and it showed that it will be so-called condition stable. So basically from here, you can see that it tally. okay, this value which is less than 1 show that it is also potential stable rather than unconditioned stable. So therefore with this, I need to plot the stability circle. So basically this is what you mean here. Okay, so how can we actually plot the stability circle? So basically this will be the center, okay, for my load. This will be my radius for my load. This will be the center for my source. This will be the so-called the radius for my source. Basically, okay, I believe how to calculate, you should be able to do it now, okay, because of the time constraint, I will not be able to show it to you step by step again, okay, but this will be the center value and the radius of the stability circle. So basically, in short, let's just concentrate on one. Okay, so this will be, okay, so before I continue on the Smith chart discussion, okay, if you find this video helpful, okay, please help to like this video. And if you have really learned something from this video, okay, please consider to subscribe and turn on your notification bell. Okay, let's go to the Smith chart now. Okay, so basically this will be the solution for the Smith chart. Okay, so how can I actually plot the output stability circle, which I will illustrate, okay, on my next slide, and this will be the input stability circle. Okay, but because this is too small, so basically I will cut them into half for visualize and then for explanation. Okay, so basically this is what I mean. I will concentrate on this zone, okay, in order to complete our discussion. Okay, so earlier on I have mentioned that let's just concentrate on the output stability circle, which is the load portion here. Okay, so basically let's concentrate on the load first. Okay, I think the source it will be quite similar. Okay, but let me just concentrate on the load first. Okay, so basically these are all the calculations that I've done earlier on. Okay, how to plot all this value? Okay, you will not have any idea. Okay, so this is in fact a common mistake by student. What is 1.59? And they are puzzled. Okay, so what you're supposed to do is firstly look at the so-called the 132 degree. Okay, so if this is 132, and if you look at this number here, so basically it's from the angle from here to here. And if you follow through this, you can see that the angle here, 30, 40, 50, 60, 70, etc. And you actually need to find 132. And you find this point, which is 130. So this point will be actually 132. Okay, so what you need to do is basically you cut from the point of origin, okay, which is the point 1, so-called of the Smith chart. You draw this line here. So basically this will be so-called the line. Okay, you draw this line first before you can actually determine all the parameters here. So next over here, okay, you see that this so-called center will be equal to 1.59. How can you do about it? Okay, because the size of the symmetry actually vary. Okay, so what you need to do is basically first thing that you need to do is you measure your Smith chart. For example, if I measure here to here, let's say it's 8 centimeter, because as I told you that if you photocopy your Smith chart, okay, the size of the Smith chart may vary. Okay, so what I need to do is basically I measure this. Okay, so basically this point here under the Smith chart magnitude is supposed to be 1. Okay, but if I measure this is 8 centimeter, which means that 8 centimeter actually represent 1. And when this is 1.59, okay, what I need to do is basically from here you can see that, okay, I actually need to plot this, okay, 1.59 multiplied by the reference point, which is 8 centimeter. Okay, as I told you earlier on, okay, so we actually do a measurement, okay, and we indicate this as a reference, which is 8 centimeter. Okay, so basically what we plot on the center of the loop is 1.59. So basically 1.59 multiplied by 8. So therefore I need to plot at 12.72 centimeter away. Okay, so basically this length need to be 12.72 centimeter, and I actually indicate over here. Okay, I hope it's clear. Okay, and then for the radius, okay, it's actually not to plot at 0.9 centimeter. Okay, so what you need to do is basically, okay, again, you need to plot this is 0.915 multiplied by the reference point, which is 8 centimeter. So your radius need to be at 7.32 centimeter. So basically from here, this is where your center point, you put your compass 1 point here, and then another point, you actually can plot this output stability circle. Okay, I hope it's clear. So basically this is how I actually plot the output stability circle. Okay, first thing, okay, will be 132, which is the so-called the degree, okay, or the degree value 132, and I actually find the 132. And then next, basically I draw a line, okay, cutting through 132 and the center point of the Smith chart. Okay, so basically this will be the first thing I need to do. Second thing I need to do is I will measure the length, okay, from this point all the way to here. Okay, I will measure the length. Let's say it's 8 centimeter. So this will be my reference point. Okay, so what happened here is basically the center will be 1.59 multiplied by 8, which tells me that it's around 12.72 centimeter. So basically from this center point, okay, so this is actually near center point. I can't plot two together. So basically imagine this is actually at the center point. Okay, all the way to here. Okay, so basically it shows that it need to be 12.72 centimeter. So this will be the center point of the output stability circle. Okay, again, how to plot the radius? Okay, I actually have this 0.915. I multiply by the reference. Okay, therefore, I actually get this 7.32 centimeter. So this will be the radius of my output stability circle. So from here, okay, you can see that I actually got the center, I actually got the radius, and basically I will use my compass to draw the output stability circle. Okay, it will be the same for the input stability circle. So first thing is 162. So you can look hard here. This is 160. It cut through at 162. Okay, so how to draw this? I believe you should be able to do it. In the interest of time, okay, I will skip this part, but I don't think you foresee any difficulty to draw this input stability circle. Okay, so over here you realize that, okay, how to determine which zone is stable, which zone is unstable. Okay, so basically from here you can see that since S11 is less than 1 and S22 is less than 1, okay, which means that the center part, okay, which is this point here, is the one that is stable. So this part will be stable, which means that the other side of this output stability circle, okay, will be unstable. So therefore, this zone will be unstable for the output stability circle. As for the input stability circle, again, okay, this part here where you actually draw, this part will be unstable. So basically from here, you can see that I actually make use of the stability circle, okay, to determine, okay, which part is stable, which part is not stable. And with this, I like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.